Now we are going to start module 2 of chapter 3. In this module, we shall discuss on some properties of nonlinear spaces. What we wanted to focus on this chapter. Here we shall discuss some results which are analog to the study of some results on classical real analysis. Now we are going to start module 2 of chapter 3 under the title Nonlinear Spaces and Banach Spaces. The module 2 consists of basic properties of a nonlinear spaces. So, before going to study the properties of nonlinear spaces, we are going to give some definitions. A linear space X over a field of scalars capital F is called a nonlinear space, shortly written as NLS, if with every element x of capital X there is associated a real number called the norm of x, denoted by this symbol, such that following axioms called norm axiom hold. That is number 1, N1 axiom, that is this is always greater or equals to 0 and this equal to 0 if and only if x equal to 0, that is the 0 vector of x. That is second axiom, that is norm axiom 2, written as N2, this lambda x is equal to mod lambda into this, where alpha belongs to f, and norm axiom 3, this x plus y is less or equals to this plus this for all x y belonging to x. Here this is a function from x to r called the norm function on x, and the pair x, this function denoted as norm function, is designated as a nonlinear space. Now, norm induces a metric on a nonlinear space. Define d x cross x to r by d x y is equal to norm x minus y, where x y belonging to capital X. Clearly, dxy is greater or equals to 0 and dxy equal to 0 if and only if norm of x minus y is equal to 0 if and only if x is equal to y. Thus, we see that dxy is greater or equals to 0 and dxy equal to 0 if and only if x equal to y. Also, dxy is equal to norm x minus y is equal to norm minus of y minus x is equal to norm of y minus x is equal to dyx, that is symmetricity axiom holds for a metric, and dxz is equal to norm of x minus z for z belonging to capital X. Thus, dxz is equal to norm of x minus z is equal to norm x minus y plus y minus z, which is less or equals to norm of x minus y plus y minus z by N3. N3 axiom is known as triangle inequality, which gives equal to dxy plus dyz. Thus, all the metric axioms are satisfied. Let us introduce a metric d x cross x to r defined by dx plus u comma y plus u is equal to dxy for all x y belonging to x. This is known as translational invariant property for a metric D. And number 2, d alpha x alpha y is equal to mod alpha dxy for all x y belonging to x and alpha belongs to capital F. This is known as absolute homogeneity property for D. Now, we have a remark that the metric induced by a norm, that is dxy is equal to norm x minus y, xy belonging to x, has translational invariant property and absolute homogeneity property. Let D be a metric on x having translational invariant and absolute homogeneity property. For x belonging to capital X, we define norm x is equal to dx theta, where theta is the null vector of x and theta is equal to 0 vector, that is the 0 vector of x. Then we say that D induces a norm on x. As D is always positive, that is dx theta greater or equals to 0, norm of x is always greater or equals to 0, and dx theta is equal to 0 if and only if x equal to theta, that is norm of x equal to 0 if and only if x equal to theta. Let alpha belongs to F, that is alpha is an element of the scalar field capital F. Then norm of alpha x is equal to d of alpha x theta by the definition of norm of x, that is d of alpha x theta is equal to again d alpha x comma alpha theta, because alpha theta is equal to theta, which is equal to mod of alpha dx theta, which is also equal to mod of alpha into norm of x. Take y is any element of x. Now norm of x plus y is equal to dx plus y comma theta, which is less or equals to dx plus y comma y plus theta plus dy plus theta comma theta is equal to dx theta plus dy plus theta comma theta plus theta. The first one comes by translational invariant property for d, and theta is equal to theta plus theta, which is equal to dx theta plus dy theta is equal to norm x plus norm y. Thus, all the norm axioms n1 to n3 are satisfied on x. A sequence xn in a nonlinear space capital X is said to be cosy if norm of xn minus xm tends to 0 as nm tends to infinity. That is, for every epsilon greater than 0, there exists a positive integer capital N such that norm of xn minus xm less than epsilon whenever n comma m is greater or equals to n. Later we shall see that real number space is a nonlinear space. In a nonlinear space, a sequence xn is said to be cosy, that is, a sequence xn in a real number space R is said to be cosy if modulus of xn minus xm tends to 0 as nm comma tends to infinity. A sequence xn in a metric space X is said to be cosy if d of xn comma xm tends to 0 as nm tends to infinity whenever d comes by the induction of norm. So, in a nonlinear space, the equivalent concept of cosiness is that for every epsilon greater than 0, there exists a positive integer capital N such that norm of xn minus xm less than epsilon whenever n comma m is greater or equals to capital N. Similarly, we take a definition like this, that a sequence xn in a nonlinear space capital X is said to be convergent to an element x belongs to x if norm of xn minus x tends to 0 as n tends to infinity, and we write limit of n xn is equal to x. In the case of reals, we write modulus of xn minus x tends to 0 as n tends to infinity. That means, for every epsilon greater than 0, there exists a positive integer n such that norm of xn minus x less than epsilon whenever n greater or equals to capital N. This concept is applicable in a nonlinear space whenever a sequence xn is said to be convergent to an element of that space. A subset B in a nonlinear space capital X is said to be bounded if there is a positive real k such that norm of x less or equals to k for all x belongs to capital B. Let x naught belongs to capital X and R be a positive real. Then in X the set collection of all elements belonging to X such that norm of x minus x naught is strictly less than R is called an open ball centered at x naught having radius is equal to R and is denoted by BR x naught. Similarly, we have a closed ball BR third bracket x naught is equal to x belonging to capital X such that norm of x minus x naught less or equals to r. That is the collection of all such elements x belongs to capital X whenever norm of x minus x naught is less or equals to r. And in agreement with usual open sphere we encounter in coordinate geometry, we have a sphere SR x naught is equal to x belonging to x such that norm of x minus x naught is equal to r centered at x naught with radius r. For sphere, rather open sphere or closed sphere, we write S, and for open ball, closed ball, we write B. So that's why we have written SR x naught and BR x naught in the respective concept of open balls and open spheres. Now let us take a definition. A sequence xn in a nonlinear space capital X is said to be bounded or non-bounded if there exists a positive constant k such that norm of x less or equals to k n. In analog of the real analysis, a set is said to be bounded if there exists a constant k such that modulus of x less or equals to k for all x belonging to the set concerned. So, there is a remark, we note this remark that every convergent sequence is cosy and non-bounded. Similarly, we get a result in real analysis that every convergent sequence in a real number space is also cosy. That means, if xn be a sequence in X such that xn goes to X as n tends to infinity. So, for epsilon is equal to 1, there exists a positive integer capital N such that norm of xn minus x less than 1 whenever n is greater or equals to capital N. Now, we can write norm of xn less or equals to norm of xn minus x plus norm of x. This is done by the triangle inequality, and which is always less than 1 plus norm of x whenever n is greater or equals to capital N. Let small k is equal to maximum of norm of x1, norm of x2 dot 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 norm of xn minus 1 comma 1 plus norm of x. So, norm of xn less than k for all n. We can consider such type of the maximum value because this set is a finite set and every finite set has a maximum. Hence, xn sequence xn is non-bounded. Also, for all positive integers n comma m, we can calculate norm of xn minus xm. So, norm of xn minus xm less or equals to norm of xn minus x plus norm of xm minus x. This is done by mutual adjustment of x and by triangle inequality, and this goes to 0 as n comma m tends to infinity, implying that xn is cosy in a nonlinear space capital X. Now, we have a theorem and which is analog to the theorem in real analysis. Let capital X be a nonlinear space and let sequence xn and sequence yn be two cosy sequences in X such that xn converges to x naught and yn converges to y naught as n tends to infinity, where x naught y naught belonging to capital X. Let alpha n is a sequence of scalars taken from F, where F being the field of scalars, be such that alpha n goes to alpha naught as n tends to infinity. So, the following holds. Number 1, xn plus minus yn goes to x naught plus minus y naught as n tends to infinity. Number 2, alpha n xn goes to alpha naught x naught as n tends to infinity. Number 3, if sequence xn and sequence yn are cosy sequences in X and sequence alpha n is a cosy sequence in F, where F being the field of scalars, then xn plus yn is a cosy sequence in X and sequence alpha n xn is also a cosy sequence in X. Also, number 4, norm of xn goes to norm of x naught as n tends to infinity. These results also hold in real analysis. We are going to prove this result one by one. For 1, norm of xn plus minus yn minus x naught plus minus y naught is less or equals to norm xn minus x naught plus norm yn minus y naught, which goes to 0 as n tends to infinity. So, xn plus minus yn goes to x naught plus minus y naught as n tends to infinity, where x naught plus y naught belonging to x, because x is a linear space. For 2, given alpha n goes to alpha naught belonging to capital F as n tends to infinity. So, modulus of alpha n minus alpha naught belongs to 0 as n tends to infinity. So, there exists a constant m greater than 0 such that modulus of alpha n is less or equals to capital M for all n. Now, norm of alpha n x n minus alpha naught x naught is equal to norm of alpha n x n minus alpha n x naught plus alpha n x naught by alpha naught x naught by suitable adjustment of alpha n x naught, which is equal to norm of alpha n x n minus x naught plus alpha n minus alpha naught into x naught, which is always less or equals to norm of alpha n x n minus x naught plus norm of alpha n minus alpha naught x naught by triangle inequality of norm axiom n3, which is again equal to modulus of alpha n norm of x n minus x naught plus modulus of alpha n minus alpha naught into norm of x naught by norm axiom 2, which is always less or equals to m into norm of x n minus x naught plus modulus of alpha n minus alpha naught norm of x naught tends to 0 as n tends to infinity, because modulus of alpha n less or equals to m, because it is convergent. So, there exists a constant m such that modulus of alpha n less or equals to m. So, alpha n x n goes to alpha naught x naught as n tends to infinity by the assumption modulus of alpha n minus alpha naught tends to 0 as n tends to infinity, because alpha n goes to alpha naught as n tends to infinity is given. For 3, since norm of x n minus x m tends to 0 as n m tends to infinity, because x n is a Cauchy sequence which is given in our theorem, and norm of y n minus y m tends to 0 as n m tends to infinity. So, we have norm of x n plus y n minus x m plus y m less or equals to norm of x n minus x m plus norm of y n minus y m tends to 0 as n comma m tends to infinity, implying that sequence x n plus y n is a Cauchy sequence in X. Since sequence alpha n is Cauchy sequence of scalars, and since scalar field is complete, sequence alpha n is convergent, hence alpha n is bounded. Also, norm of alpha n x n minus alpha m x m is equal to alpha n x m minus alpha n x m plus alpha n x m minus alpha m x m by the mutual adjustment of term alpha n x m is equal to norm of alpha n x n minus x m plus alpha n minus alpha m into x m, which is always less or equals to modulus of alpha n norm of x n minus x m plus modulus of alpha n minus alpha m norm of x m tends to 0 as n comma 10 tends to infinity. Since sequence alpha n is bounded and sequence x n is norm bounded, alpha n x n sequence alpha n x n is a Cauchy sequence in X. For 4, the proof of 4, for x y belongs to capital X, norm of x is less or equals to norm of x minus y plus norm of y by triangle inequality axiom number n3. So, this implies norm of x minus norm of y is less or equals to norm of x minus y. Interchanging the role of x and y by norm axiom 2, we have norm of y minus norm of x less or equals to norm of y minus x, which is equal to norm of x minus y. So, combining this, modulus of norm of x minus norm of y is less or equals to norm of x minus y. Thus, modulus of norm of x n minus norm of x naught less or equals to norm of x n minus x naught tends to 0 as n tends to infinity. So, norm of x n goes to norm of x naught as n tends to infinity. Thus, in module 2 of this chapter 3, we have an overview about the definition of a nonlinear space and some of its basic properties. We have learned the Cauchy sequences, convergent sequences in this nonlinear space. Similar results can also be obtained in a real analysis regarding the Cauchy sequences and convergent sequences. So, all the results what we get in classical results can be generalized in a nonlinear space. Now, we are going to talk on further properties, that is basic properties on such a space called nonlinear space. We have learned that norm is a function. So, by 4 of the above theorem, we see that if x n goes to x naught as n tends to infinity, norm of x n goes to norm of x naught, and we say that the norm function is continuous. In classical analysis, that is real analysis, a function f is said to be continuous if x n goes to x implies f x n goes to f x as n tends to infinity. Now, we take a definition. A nonlinear space capital X is said to be complete if every Cauchy sequence in X is convergent to an element of capital X. Let us take another definition, that a complete nonlinear space is called a Banach space. Equivalently, a Banach space is a nonlinear space which is complete with respect to a metric induced by a norm. That is, if we take dxy is equal to norm of x minus y, where xy belonging to the nonlinear space capital X. Now, we get a theorem, if capital L be a subspace of a nonlinear space X, then its closure L bar is also a subspace of X. The proof is like that, let x y belongs to L bar, that is x y is an element of L bar. So, corresponding to epsilon greater than 0, there exist elements x comma y belonging to capital L such that norm of x minus x1 is less than epsilon and norm of y minus y1 less than epsilon. For non-zero scalars alpha comma beta, norm of alpha x plus beta y minus alpha x1 plus beta y1 by mutual adjustment, we get that this is less or equals to modulus of alpha into norm of x minus x1 plus modulus of beta norm of y minus y1, which is strictly less than epsilon into modulus of alpha plus modulus of beta and taken as epsilon dashed say, implying that alpha x1 plus beta y1 belongs to b epsilon dashed alpha x plus beta y, where b epsilon dashed alpha x plus beta y is the open ball centered at alpha x plus beta y with radius epsilon dashed, where alpha x1 plus beta y1 belonging to capital N and b epsilon dashed alpha x plus beta y is an open sphere centered at alpha x plus beta y with radius is equal to epsilon dashed. Thus, alpha x plus beta y belongs to L bar. So, thus we get a following theorem, if capital X be a Banach space and capital L be a closed subspace of X, then L is again a Banach space. The proof is like this, if capital L is a closed subspace of X, then L becomes a closed set of a complete metric space, the metric being induced from the norm on X. And we know that every closed subspace of a complete metric space is a complete metric space, that is a metric subspace. It follows that L is a Banach space as a subspace of X. Thus, what we have discussed in module 2 of this chapter 3, that is, we have an overview of a concept of a nonlinear space, some results on nonlinear space and some examples of it. Also, we have acquainted with the Cauchy sequences and convergent sequences. Also, we have learnt a Banach space, that is a complete nonlinear space and its subspace.